My name is Gianluca Gerard. I work as the Chief Technology Officer at TensorFlow, and I am mostly involved in deep learning projects. So today we will try to cover deep learning in general, what deep learning is, and we will also try to cover a little bit of TensorFlow. So TensorFlow is an open source library which is mostly used for numerical computation, and is particularly well suited for machine learning in general and deep learning in particular. TensorFlow has been used in a number of projects. I'm listing here just a couple of them, both of them in the medicine field, in the medical field. This one is a work published at the beginning of 2017. This group of scientists at Stanford, they used a TensorFlow architecture basically to classify skin lesions and to recognize melanoma on skin. Another project, this time at Google, TensorFlow has been developed at Google. They have been able, with images of the eyes, to recognize whether or not the patient has diabetic retinopathy or not. So, as you can feel almost immediately, with the introduction of deep learning and TensorFlow, computers have been able to do something which was prior to deep learning almost impossible to do. So it was really a paradigm shift which is happening right now. Before delving into what TensorFlow is and how it works, let me take a step back and discuss about what is machine learning and what is deep learning. In order to understand what machine learning is, I think it's important to think about what a classical program is instead. When you have a classical program, when you write, I bet most of you are programmers of some sort, or you are probably able to program traditional computers. Well, when you are writing a program, what you do, you take a set of rules, set of instructions someone gave you, and you translate those set of rules into code. And that code will then take data and transform the data into answers. So, for example, let's think about a program which takes a paragraph, a list of words, and it counts the number of words in that paragraph. Okay? So, very simple program. Everybody of you probably will be able to write such a program. Very simple. But you have the algorithm, you have the data, and you get the answer. The answer are the number of words into that paragraph. Instead, with machine learning, the paradigm is completely different. With a machine learning algorithm, what you give to the algorithm, to the program, are examples. And the more examples you have, the better. What is an example? An example is a pair of data and answers. So someone else gave you, for each paragraph, the corresponding number of words in that paragraph. And you have many paragraphs, so many examples. And for all those paragraphs, you have the number of words in that paragraph. You pair them together, and you keep passing those examples to your program. Eventually, your program, your algorithm, will be able to find the rules to associate the number of words in that paragraph with the word count. So the machine learning output, in reality, what we are interested in are those rules. And why is that important? Well, because there are a number of problems, like, for example, image recognition, finding the object inside an image. I bet nobody would be able to program a computer directly, explicitly, in order to recognize a cat or a dog in an image. Well, with machine learning, now we are able to. And this is really the big difference with what we had just a few years ago. In particular, we have been able to classify images thanks to artificial neural networks. Well, this is a very high level and schematic representation, obviously, of an artificial neural network. I think that the concept that you have to take home from this representation is that neural networks are a set of neurons, and each set is called a layer. So the box that you can see here, unfortunately I cannot point to it, but you see, this one is a layer, this is another layer, and so on. And all those layers are connected by what we call weights. Each layer, what each layer does is simply a transformation, is a mathematical transformation of numbers. So, first concept to remember, when you're using artificial neural networks, you have to transform your data in some way, and this is the key part, this is really the difficult part, to be honest. You have to transform in a proper way your data into numbers. Once you have a mathematical or a numeric representation of your data, then you can start applying those transformations. And a typical transformation that we do now is, for example, we take an image. An image is very easy to transform it into numbers because it is a matrix of numbers, basically. We can transform it, and once we get the final answer most of the time is a probability, or can be read as a probability. And that probability is the probability of that image to represent a particular class. This is really a classic example of usage of deep learning. What is a neuron? So we said that a neural network is composed by neurons. A neuron is, again, a mathematical object, very simple one. What a neuron does, it does a weighted sum of the inputs. As I said at the beginning, we have to transform your data into numbers. So your input will be numbers. A neuron, what it does, it takes those numbers, it transforms those numbers with a weighted average, and then it applies to that weighted average a function. Typically, this function will be non-linear. So it will be something like a sigmoid, S-shaped function, or stepwise functions. Those are the functions which are generally used in machine learning. But as you can see, very, very simple mathematical operation. But yet, if you stack enough layers of enough neurons, like in this case, this is a representation of what is called the inception version-free neural network. This is exactly the neural network which was used by those researchers at Stanford to classify skin lesions. You see, I mean, it's just a number of layers, one after the other. And believe it or not, this network, to these days, has better performances than humans in recognizing objects in images. So a human will make more errors judging what is in an image than a computer using such kind of network. So a revolution which started about in 2014. Okay, so this is a typical deep learning neural network. Why deep learning has been so successful? Well, because deep learning, which is a subfield of machine learning, has the peculiarity of improving the performances the more data it sees. I said at the beginning, machine learning is able to create the rules, and the more data you have, the better. That is partially true for classical machine learning. For classical machine learning, at a certain point, the performance does not improve. With deep learning, instead, your performance keeps improving. So more data you have, and these days, more data generally in many fields, maybe not the medical field, but in many fields, is always available. And this is the reason now we have speech recognition, language translation, image recognition, you name it. All sorts of things that just a few years ago looked like sci-fi. But as I promised, we're not discussing in general about deep learning. I want to give you a sense of what TensorFlow is and what TensorFlow does. In particular, I want you to go back at home with really the key ideas that you have to know in order to start writing TensorFlow programs. And the very first concept you have to take home is that a TensorFlow program is different from a regular program. And the main difference is that you do not write code like the one in blue above, which is pseudo language for any kind of programming language. In TensorFlow, the first thing you have to learn is that a TensorFlow program is written in two phases. Phase one, you build a computational graph, and we will see in a moment what a computational graph is. Once you have built this computational graph, then you can use or execute your computational graph to obtain your results. Let's see what a computational graph is. Okay, so obviously this is a graph. A graph is a set of nodes connected by arrows. Each node is an operation. It can be a mathematical operation, or it can be some sort of transformation of your input data. The data flows in the arrows. And a way to use a computational graph like this one, which this computational graph, what it does is exactly the same operation that you see in the second row of the pseudo language. So we add together the multiplication and the summation of two numbers, basically. What it does? Well, basically, let's suppose that I already built with TensorFlow a computational graph like this one. When I execute the graph, I give the input to my computational graph. So, for example, I give to node A and B two values, 3 and 7. A and B will just pass along those values to the next nodes, to the next layer. These other nodes will perform the mathematical operations. They will give back a result, which will be the input to another node, and finally we get the final result. Okay? So at this point you are probably wondering, what the heck, why shall I go through all the complexity of building such a graph and so on? I hope it will become a little bit more obvious as we go into some example. But for the moment, let's just remember the fundamental concept. In TensorFlow, first of all, you build a computational graph, and then you pass data to that computational graph in order to obtain your results. How do I build a computational graph like this in TensorFlow? Well, it's very easy. You have in Python, this is an example of using TensorFlow in Python, which is very, very typical, but you can use TensorFlow in Java, C++, you name it. First of all, we import the module as TF, and then we can add nodes to our graph. So the first two lines, TF constant, the two TF constant calls will add to my graph, to my default graph in TensorFlow, two nodes, node A and node B. We have seen it a moment ago. So, sorry. We are adding node A and node B. Then we are adding the rest of the graph. So we are adding the multiplication node with this call, multiply. We are adding the other node, add. And then we are taking the output of these two nodes and we are adding the output together. At this point, we have the graph. It's already built. Very simple. And as I said, now I have to run the graph. In order to run the graph, this is boilerplate code that you will always see in TensorFlow. You initialize a session, and the reason why you initialize a session is because a TensorFlow graph can execute on CPU, central processing unit, and graphical processing unit, and then you run and you get the results. Another important concept that you have to take home from this presentation is that data in TensorFlow can be a lot more complex than simple numbers. You can pass matrices, vectors. They are all called tensors, okay? A matrix is a two-dimensional tensor, a scalar is a zero-dimensional tensor, and so on. So RGB images are cubes because we have a stack of 3 matrices, 1 matrix per channel, red, green, and blue. When we pass batches of data to a TensorFlow graph, because we want to take advantage of the parallelism of graphical processing units, what we assemble together are batches of images. And so they become 4 cubes, because we have an index as the first dimension, the index of the image, then we have the channel of the image, red, green, and blue, and then we have the matrix, the luminance of the pixels. And so, once we have this concept of tensors, all those operations, all those nodes that we have seen before, they become all more powerful because we can multiply together the matrices, and we can multiply together the vectors. And so you can start to get a feeling that with massively parallel architectures that we have on graphical processing units, we can speed up enormously the computations that we can do. And this is one of the reasons why deep learning is possible now, and it was not possible 20 years ago. We didn't have such powerful architectures, such multi-parallel architectures available. One other concept that you have to learn in TensorFlow is how to pass data to your graph. We have already seen the usage of constants, so we are basically adding the values into the graph itself, but obviously we want also a way to pass external data to the TensorFlow graph. And the way to do it is by using placeholders. A placeholder is a promise that I will pass to the graph a value, an input with a certain shape and a certain type. And another very important concept to remember is that we can include into the graph the variables. The variables are the weights, are typically the weights of the artificial neural network. These are free calls that are used to do that. Let's take an example. The code is becoming a little bit more complex, but in this case, this is the simplest neural network you would ever be able to write. It's a neural network with just one layer and one neuron. And what it does, it's very simple. It takes an input, x, it multiplies that input for the weights variable w, it adds a bias b, and it applies a function, the sigmoid. So we are defining the input, the promise to pass a certain type with a certain shape, a vector of 3 elements. We are multiplying that x by the weights. We are creating the bias. We are multiplying those together here. And finally, we are applying the function, the nonlinear function. And once we have built our graph, we can run our graph by passing explicitly the data in this way. And so this will be the input of my neural network, and this is going to be the result. So, obviously, with TensorFlow, we can do a lot more. Unfortunately, we do not have time to go into the details, but one example of what we can do with TensorFlow is, for example, linear regression. This is the toy example which is used to understand what TensorFlow can do. Linear regression is an algorithm which is able to predict the value of something based on the input data. In this case, we can try to predict the value of houses in California based on input parameters. These are the input parameters. We have 20,000 examples. And this is what linear regression is in mathematical terms. So we create a matrix of input data, X. We have a target values, the house values, which becomes the vector Y. We have the model, our weights. The model are our weights, the weights that we have to find, the weights that will provide the best prediction of the house values, basically. How do we use those weights? In linear regression, very, very simple. We just multiply the input data, X, by the weights, and that will give the prediction of the house values for all the input data. Then, in order to see whether or not our weights are working, we simply take the difference between the prediction and the actual value, and we try to minimize, we try to find the weights that minimize this cost, this distance between prediction and actual values. How do we find the optimal weights? Well, we use this algorithm, gradient descent, which is the simplest one. Basically what it does, it keeps updating the weights, theta, until we reach a minimum, a local minimum of our cost function, j, the distance between prediction and actual values. Scary in a sense, but what it does, for example, gradient descent is useful. For example, we are iterating and we keep changing theta, the weight, until we fit, for example, this set of data. For our actual example, the way to use TensorFlow in order to get a gradient descent is this one. First of all, obviously, we load the data. Once we load the data, and I don't assume that you will be able to follow, but I mean, this is simple in a sense. You load the data, and then you create the training matrix, the one which we called X at the beginning, and the target vector, the vector with the actual values of the houses. We create the graph. The graph is composed by the input matrix X, the target value Y. What we do, we create a matrix of parameters, the weights, the theta weights, and then we say that the prediction will be the multiplication, the matrix multiplication between the input data and the weights. And this will give us our prediction. The loss is just the mean square error between the prediction and the actual values. These few lines of code have all defined the graph which defines the linear regression model. We don't need anything else. The magic that we get for free with TensorFlow is this one. You remember, in order to find the optimal weights, we had to use the gradient descent algorithm. But the gradient descent algorithm says that we have to compute the partial derivative of the cost function with respect to the weights. And I bet not many of you would be content to write that by hand, especially if the loss function is really complex. And the loss function sometimes is really complex. But with TensorFlow, we get this for free. So we have just to ask for an optimizer. This is the term which is used to define this algorithm. The gradient descent is an optimizer because it finds the optimal weights for our model. And then we have just to apply this optimizer to our loss function. Automatically, this simple line will add to our graph all the mathematical transformations which are needed to compute the gradients and so the derivatives, and also the steps necessary to update our weights. So at the end, in this Python variable training underscore hop, we have a handle to the graph which will execute the gradient descent. So the operations which will find the optimal weights. We don't have to do anything else. So it's very, very powerful. I mean, very, very convenient. The way to use it is always the same. Once we have defined the graph, we initialize a session, we initialize the variables. This is necessary because if you start with the variables which are just 0, you will not be able to learn. So you have to initialize those variables randomly in a proper way. But then you just keep iterating the training operations. So you keep changing your weights by continuously passing your 20,000 examples, and eventually you will be able to find the optimal theta. And this is an example of what you get. So after 100 epochs, after 100 iterations, I have already fitted my line as before. Now obviously I don't just have one single input value, I have 9 input values, but I found the optimal linear approximation to those 9 values. And hopefully, if I use these weights in my model, I will be able to predict the house values correctly. So very, very simple example, obviously. I know it's not a neural network, but neural networks are built exactly in the same way. Exactly the same concepts that I have shown here are the ones used also to build Inception V3, every kind of networks. So I really hope that now you have at least a few basic concepts. Just to recap, what are the key ideas that you have really to take back with you? First of all, machine learning is a paradigm shift. You learn a model from the data. You learn the rules. And sometimes we do not know the rules to solve a certain problem. So we have to rely on machine learning to find the rules. TensorFlow, remember, keep always separated the computational graph from its execution. First of all, you build the computational graph and then you execute the computational graph. And also remember that in TensorFlow, tensors are data, but TensorFlow, the big advantage of TensorFlow is that it is able to parallelize the flow of that data, so it's very fast, very efficient, and it gives you for free all sorts of optimization algorithms, and that is very, very obviously useful and very, very efficient. Gradient descent is one, but there are a number of them, very, very complex, and it would be difficult to build those algorithms by hand. And well, here we have a few resources that I would suggest if you're interested to know more about it. There is a very good machine learning crash course by Google that you can access. There is a TensorFlow blog, which is also very good. And there are a number of resources that you can use from Google directly. Unfortunately, the TensorFlow documentation is not very good yet because it keeps changing. So in order to learn, better to use these other resources. I don't know if we have time for questions. Do we? I think so. So, go ahead.
In the previous example, why do you choose a lower value of learning rate?
I chose a learning rate such as this one. So if I understood the questions correctly, why I chose this learning rate, yes, right? Which is very, very small as a learning rate. Well, because this is really a toy example. What I'm doing here, so we can go back and look at the beginning of our toy example. What we are doing here, we are loading all the data together. Okay, so I'm loading, just for the sake of the example, all 20,000 examples together. All right. And so what I'm actually using here is not stochastic gradient descent, which is generally used, but I'm using the gradient descent proper. So I'm passing to my model all the data together. And if I would choose a higher learning rate, basically I would not be able to find the local minimum. The step I would take would be too big in changing my weights. The learning, how do we use the learning rate? Let's go back to this equation. To this equation. The learning rate is used here for the update of each weight. Okay, and this step, what it does, it changes my weight by a fraction of the gradient of the cost function with respect to that weight. The cost function is computed by default on all the data set. So if I pass all the data all together, well, I will basically get a bigger cost function. And if I would use a learning rate which is too big, basically I would change the weight too much. And I would risk to make a step which is too far away from the optimum, okay? If I take a lambda, a learning rate, which is small enough, I don't risk to move on the other hill, basically. I will just take a baby step, hopefully in the right direction. And this is the reason I had to choose for this example a very small learning rate. In reality, what is generally used is what is called stochastic gradient descent. Stochastic in the sense that instead of passing at each iteration all the input data, you only pass a batch of data to your gradient descent algorithm. So you have less data to pass and you can use a larger learning rate. So I hope I tried to answer your question. Other questions? Go ahead.
Can we define some custom function with an algorithm? Which language do we need to use? This language or even other languages?
Well, so I believe the question is, how do I define, how do I program the cost function, right? Okay. Well, in TensorFlow, yes, you have to use TensorFlow because this is actually a part of the graph. So this cost function here becomes a part of the graph. And you can see it, you see, this is the mean squared average between the prediction and the actual value, all right? So this is what we have to compute. And if we take a look at our program, we are defining the cost function here. You see? The loss, our J, is this node, basically. Obviously, this is a complex node because we are basically taking the output of this matrix multiplication. We are subtracting. Obviously, in TensorFlow, thanks God, we have operator overloadings. So the minus here, in reality, will add a subtraction operation into my node. So this one will become a node, which will provide an output to this other node, which will create the square. And the output of the square node will become the input of another node, which will sum up and divide by the number of rows which have been, which are the results of these square operations. So as you can see, I used TensorFlow calls to add nodes to my computational graph. Remember, everything in TensorFlow is a computational graph. And so also my cost function, which is also called loss function, is created in this way by adding the proper nodes to the computational graph. And the reason I have to do it in this way is because I then want to take advantage of these optimizer operations. You see, this optimizer object, what it does it tries to minimize the loss function, right? So I have to pass a part of the graph to this other function, and this other function will do all the magic for us. It will literally, if I would print out the graph, the final graph of TensorFlow after this call, we would see all the nodes which are basically implementing the gradient descent. So I would really literally find for every weight these operations added to the graph, because those are the operations that we have to do in order to find the optimal weights, the weights which minimize our cost function. So a long answer to a short question, but the answer is you have to add the nodes to TensorFlow. Obviously, you can use other languages, but in any case, you have to use function calls into TensorFlow in order to do it. Okay? Any other questions? Don't be shy. I hope I left time for this. Anything unclear? Go ahead.
Is there a graphical editor of this?
Yes, there is, absolutely. So the question is there a graphical editor to see the nodes? Yes, there is. It is called Tensor Board. So within TensorFlow, what you do, basically, there are functions that you can call, and it will save the graph for you. And then there is this other program, which is part of the TensorFlow framework. You start the Tensor Board server, so to speak. Then you can access it via web on your host, and this little program is able to look at the data that you have saved, at the graph that you have saved, and it will give you a graphical representation of all the nodes and all the arrows, and sometimes obviously it can be very, very complex, but for debugging purposes it is also very useful. And Tensor Board, by the way, it is not just used to represent the graph, it is also used to look at the loss function. Because when you are training a real model, you want to make sure that your loss function keeps decreasing when you are performing the training. So the training is performed in steps, what are called epochs, like this one, you see, the time is passing by, and in this case the epochs are really an iteration, so we are iterating 100 times, and we are executing the weights updates 100 times. Obviously we want to make sure that our loss keeps decreasing as we progress through the training, and one way to look at it is by using Tensor Board, so you can get a graphical representation of your loss function. So if your loss function, instead of decreasing, stays constant or increasing, you know that there is something wrong in your model and you have to work out it. For example, if I would have used a larger learning rate, so for example, if I would have used 0.1 or 0.01 as a learning rate here, most likely my loss function would have done something like this. It would have started from a certain number, it would have increased, then decreased, and we would not have been able to minimize it. And with Tensor Board, obviously we would have found the issue almost immediately. So this is another advantage of that tool. Yeah, Jacopo?
I'm not sure if it's a meaningful question, but
I'm sure it is.
Why did they choose a graph? I mean, why the graph is the best fitted architecture?
That's a very good question. So the question is why the graph? Why the concept of computational graph? What is the advantage? It's a very good question. Well, the reality is that not all deep learning frameworks use the concept of the graph. For example, Torch does not. I think it's very, very useful because basically the clear advantage is that it is very easy to take this graph and move this graph into whatever system architecture, hardware architecture you have in order to execute your computation. As I said at the beginning, TensorFlow is very well suited for deep learning, and the reason is because it is able to run your numerical computations on graphical processing units. And graphical processing units are highly parallel architectures, which are obviously very difficult to program directly. But if you think about a graphical processing unit as something which is able to perform mathematical transformations, so where each core in the graphical processing unit, and maybe you know that a graphical processing unit has thousands of cores available, all able to perform mathematical transformations, well, now it becomes clear that it's very easy to map a node which does a mathematical transformation onto a core and use really the graph and the concept of moving the data through the graph to basically map very easily your graph onto a portion of your GPU. And if it happens that your GPU has more cores than you have nodes, well, the better, because you can parallelize almost immediately your iterations. You just duplicate your graph many, many times until you have used basically all the cores of your graphical processing units. So I think that from an implementation point of view, it can be very, very efficient, and in fact it is very, very efficient, and this is one of the reasons of the success of TensorFlow. From a programmer perspective, obviously there is a small price to pay, which is the complexity of having to think about graphs and execution. And the real problem, to be honest, is debugging. Debugging a TensorFlow program obviously is not as easy as debugging a traditional program. Now there is in TensorFlow another option to program which is called eager mode, which partially solves this issue. But eager mode is not very efficient in production, but it can be useful during development. Thank you. Any other questions? Yeah.
How should someone proceed in designing a topology of a graph given a certain problem? I mean, which is the process, the mental process that leads to a certain graph?
Yeah. Again, a very, very good question. So basically, to summarize, how do I come up with the right architecture in order to solve a specific problem? Well, to be honest with you, until recently, the answer was by luck. In a sense that obviously there are a lot of research papers. So what you tend to do is you do what someone else has already done, has already invented, and it is an iterative process. So it started in 2010 with convolutional neural networks. The first architecture, AlexNet, was of a certain kind, and people started to learn how to create a network for image recognition. And then someone else improved on that architecture, and then someone else again improved again. So across the years, now we have available at our disposal already a predefined zoo, literally zoo of architectures, and by experience people knows that certain architectures are better suited for certain tasks than others. So typically now what happens is that you have a business problem to solve. you know that for that business problem, that particular architecture is better suited to solve your business problem, you basically apply the architecture which someone else has built for you. What you are doing in reality is what I said at the beginning. The real issue, the ingenuity that you need to put is obviously find the right architecture, but also find a way to transform your data into numbers so that you can use that architecture. But the architectures, most of the time, are already predefined. Obviously, if you are a researcher, you work in university, obviously you also create other architectures that someone else will be able to use. With that, I think it's over. So thank you very much.
Thank you very much.